With no further ado, John, would you like to introduce tonight's speaker?
Sure would. Melissa, while I am introducing you, feel free to go ahead and grab the screen again. Melissa Morris is a fourth-year PhD student at UW-Madison, and it is Melissa who is working with her advisor, Eric Wilcots, not next month's speaker, so I boo-booed about that. Melissa is going to talk to us tonight about her research, and I'll let her introduce herself more, and I'll let her introduce her research. But I want to point out for any of you that may have already heard her, one of Melissa's passions is outreach and education. And you, Melissa, you were doing or are still doing a weekly segment on WORT radio. Maybe you want to. Go ahead.
Yeah, sure. So it's like a 5-minute segment. It's something that all of the grads at UW's astronomy department kind of collaborate on. So we kind of switch off week to week. But yeah, I think it airs every Tuesday evening at around 6 p.m. They have like a weekly news segment that is about an hour, and so we call ourselves Radio Astronomy. And so yeah, you can just tune in. I think they also have episodes on like WORT's website, so if you want to take a look at past things, this has been going on long before I got here, so there are tons of previous episodes all just talking about things from exciting astronomy discoveries all the way to like really like highlighting cool astronomers and the work that they do.
Well, when you say it's been going on for a while, let me just tell you that we have evidence of an MAS member, a woman named Paula Berner, who was doing radio programming in 1938. So it has been going on for a while. You're in good hands. You're in good company. So awesome. The other thing about Melissa that I'll mention is that she's a dog person. So I instantly liked her when I met her. We're very, very happy to have you with us tonight, Melissa. Just one more comment. Melissa, are you okay with people asking questions in line, or do you want people to hold off until the end and ask questions at the end?
Feel free to ask questions whenever you have them. Just feel free to unmute. If somebody types a question in the chat, would you be able to read it out for me? Because I don't know if I can actually easily see the chat.
I'll be monitoring the chat just for that reason. So if there's a question there, I'll pop it into you during when you take a breath.
Okay, sounds good.
Okay, so Melissa, the floor is yours. Thank you.
All right. Well, thanks so much for that introduction, John. And it's nice to meet all of y'all. Like John said, I am a fourth-year grad student at UW-Madison. So I've been here for quite a while. Originally, I come from Texas, so definitely a bit of a change in terms of weather. But I've been here 4 years. It's fine. My first year was when the polar vortex was happening. So it was a rude awakening, but you know, we're here now. I'm dealing with it. It's great. So yeah, I am going to be talking a little bit about my research. But first, I wanted to kind of introduce myself. John mentioned that it might be fun to... Oh, no. Oh, we're fine. Huh, okay, sorry. It might be fun to kind of talk about myself and just kind of tell you all a little bit about my road to astronomy and how I got where I am. So honestly, I didn't know I wanted to do astronomy until I would say I started undergrad. I came in originally as a chemistry major thinking like, oh yeah, I'll just be a pharmacist. There's job security there, right? That's fine. But then literally during orientation, I realized, wait a minute, that's so boring. I don't want to do that. I want to study space. Because it had always been a passion of mine. I'm a giant nerd. I love Star Wars, Star Trek. And so the universe has always been something that I found really interesting. And I thought, hey, why not try to study space? And I got really lucky because I did my undergrad at the University of Texas at Austin, which has a pretty big astronomy department. So not only do they have that, but they also have the McDonald Observatory out in West Texas, which is amazing to go to. These are actually a few pictures from the observatory itself. So here, let me see if I can turn on a little laser pointer. Hey, all right, great. So yeah, so here are just a few pictures. So this is actually a picture of me, my first trip to the observatory. There I am. Fun fact, the person taking this picture was using flash and told everybody, hey, close your eyes so I don't ruin your night vision. So that's why my eyes are closed. Nobody else listened, but hey, their loss. I kept my night vision. Anyways, so yeah, so this was actually a picture taken in this little room right here. We were using one of the smaller 36-inch telescopes. And yeah, McDonald Observatory, I hold it near and dear to my heart. I worked there for a summer doing a lot of outreach, giving people tours of the telescopes themselves. Here, I think I just have more pictures. Fun fact, so this is a larger telescope. I think it's like 108-inch diameter mirror. And fun fact, this mirror actually has 6 to 7 bullet holes in it because of course, Texas, it would. Anyways, if you want to know more about that, you can ask me later. But yeah, and I would give people tours of this telescope and tell them about it. And that was a lot of fun. I also got to use it a few times during undergrad, which was really exciting. And so naturally, I just kind of fell in love with observational astronomy. I love looking at the night sky. I love doing things like that. And I also love studying the universe. So that's fun. This is just a cool view this is me longingly looking at the sunset on top of the mountain where the observatory is out in West Texas. And here's just some pictures of us looking at the solar eclipse that happened a few years ago. So that was pretty cool too. So in undergrad, I got started with research pretty early. I actually made this image, or I guess this like little video right here. This is just kind of like a sneak preview, because if anyone's gonna understand or like appreciate a cool astronomy video, I imagine it'll probably be you guys, right? So what we're looking at here is you're actually looking at, this is a disk galaxy, so kind of like our Milky Way, but we're looking at it from this edge. So that's kind of why it looks like a weird little pancake. And what you can see in this simulation is there are a few other galaxies that are kind of falling onto it. And this is just looking at where the matter is itself. But this is kind of tracking gas coming from the galaxy. And so what we're seeing, one thing that I did this summer was just kind of looking at seeing, okay, how does this galaxy interact with its surroundings? And this is kind of something that I don't want to talk too much about now. If you're curious about it, of course you can ask. But this has kind of led me into being really excited to learn about galaxies specifically. I'm curious to look at outside of our own Milky Way and learn, how do galaxies evolve? What kind of things do they do that make them look the way they are? And especially, how do they interact with their larger environments? Because that's a really big question that I think astronomers have only just now started to really ask. So yeah, and this was all done at the Space Telescope Science Institute in Baltimore. And if you don't know what that is, it's a NASA contractor. They're basically the ones that take care of Hubble and James Webb. So it was really cool to work here. This is actually a picture of me standing in front of the actual James Webb like unfolding mechanism. So that was super cool. This was taken at Goddard Space Flight Center. So really exciting to see that. Now, of course, it's millions of miles away. So taking pictures, excited to get some more data from that. That'll be really cool. But yeah, so let's see. Oh, and then just about me, of course, like Sean mentioned earlier, I am absolutely a dog person. I love putting my dog in stupid little hats because I love him. He hates them, but it's okay. I don't do it too much, I promise. I don't torture my dog. But yeah, outside of astronomy, I really love hiking and going cool, fun places outdoors. I also really love kayaking, which is really great to be here in Madison because you can go kayaking anywhere as long as it's, not when the lakes are frozen. But yeah, so really excited about that. But yeah, this is just a little bit about me. I also like playing video games. I don't know. I like to do things outside of astronomy is what I'm trying to say. So yeah. So it's just kind of a little bit just all over the place about me. It was kind of chaotic, but that's just kind of who I am. All right. So now let's talk about some actual science because that's what we're all here for. Let's learn about science. So I study galaxies, as you probably got from things that I mentioned earlier. I'm really excited about learning about galaxies and why they look the way that they do look. And so here are a few different images of different kinds of galaxies, and it shows that they all come in all shapes and sizes. So we have spiral galaxies, much like our Milky Way. We have elliptical galaxies, which are just big, puffy galaxies. And then we have all sorts of other galaxies that are somewhere almost in between the two. We might see galaxies that are interacting with each other gravitationally, and we might even see dwarf galaxies. They're really common, but really hard to observe just because of how tiny they are. I mean, like, this barely looks like anything, you know? And of course, we have our Milky Way here. How could we forget? But yeah, galaxies come in all shapes and sizes. Now, not only that, but galaxies also come in all kinds of environments. Galaxies can be fairly lonely, like this galaxy, which is pretty isolated, not a lot of neighbors around it, it's just kind of floating alone in space. Or you can have something like this, which is a galaxy cluster. And galaxy clusters can be surrounded by thousands and thousands of other galaxies, and they're super duper massive. And you can also get galaxies that are somewhere in the middle. And in fact, you tend to get galaxies that are in this weird environment known as a galaxy group. It's not quite isolated because it does have a few galaxy neighbors, but it only has around like tens of neighbors as opposed to thousands and hundreds of neighbors like you would expect to see in a galaxy cluster. And so they're kind of somewhere in the middle, but what's really important about galaxy groups is that the majority of galaxies in our universe actually exist in an environment that is a lot like this. So understanding galaxy groups and what these environments themselves are like can help us understand the environments that the majority of galaxies in the universe are existing in. And so let's talking a little bit more about the overall structure of our universe. You might have heard of the cosmic web. So this is generally how galaxies and how we observe galaxies to be laid out in our universe. So this is just like a really cool video made by the Sloan Digital Sky Survey, which is this big collaboration that basically did this all sky survey that was able to really precisely measure galaxy positions, not only like in the sky, but also how far away they are. And what they were able to find is that the positions of galaxies actually take on a very particular structure, this web-like structure. So it's kind of hard to see in this video. It's just a fun video. But when we, hold on. When we look at data, such as this from the Sloan Digital Sky Survey, we can actually start to see this filamentary structure, kind of like what we were talking about. So this is an interesting map. So kind of as you go further and further away from the center, we're at the center of the circle. And as you go further and further away, you're basically looking at galaxies that are further and further away from us. And we see a lot of substructure here. We see a lot of these, you kind of see these red regions where there are these really dense areas, and these are probably where galaxy clusters exist. But one thing that you might notice when you start looking at enough of these red regions is that there are actually these kind of arms, these filaments that extend from the galaxy clusters themselves. And these are called cosmic web filaments, but they kind of act like this weird spider web structure. And it's generally along these filaments that material can then fall from somewhere out in space along the filament onto this large massive galaxy cluster. And in these filaments is where you might expect to see something like a galaxy group. And then, of course, you also have these larger voids in space where you don't see a lot of galaxies. You only see a few galaxies. And that's not necessarily what I'm going to be focusing on. What I really care about is these galaxy groups that maybe exist in this filamentary structure of the cosmic web. All right, so why am I telling you about all of this? Why do we care about the environments of galaxies? Well, it turns out that galaxies in different environments have different properties. For example, and something that we can literally just see by looking at these 3 different images of galaxy groups or galaxy clusters is that galaxies in dense regions of the cosmic web generally don't form a lot of stars. So one thing you might notice as you're looking at these images is that you're seeing a lot of these galaxies, and these galaxies kind of look yellowish, reddish. They kind of look big and puffy. And it turns out that just by looking at the color of light that we see from a galaxy, we can actually determine how recently it's been forming stars. And the reason for that is because stars that are big and blue tend to not last very long. They tend to last maybe on the order of like millions of years, as opposed to redder stars, which tend to last billions of years. So if we're looking at, say, a galaxy that is really blue, we can think, oh, there's a lot of really active star formation going on because we can see a lot of those really young blue stars. But when we're looking at galaxies like these that are redder, we call them red and dead galaxies because they're not actively forming stars. And it turns out we generally really only see these in dense environments. I mean, we might see a few that exist outside of environments that are clusters and groups, but for the most part, they only exist in galaxy clusters. And so this kind of brings me to the first question that my research is trying to address. Question 1, why aren't they forming stars? Why aren't galaxies that are in these dense environments like forming as many stars as they would if they were just in a void of space? What's going on here? There has to be some sort of physical process that is shutting off star formation in these kinds of galaxies, or that shut it off a long time ago. So this is question 1. So there are 2 questions that my research is really trying to answer. And the second question may seem a little bit tangential. So you might have seen a pie chart that looks similar to this. This is just a really fancy version of the pie chart that I found with a quick Google search. Thanks, NASA. But this essentially shows the makeup of the universe. We know that the universe is roughly 68% dark energy. Dark energy doesn't look like this. Dark energy doesn't look like anything. This is just like a fancy artist's rendition. So just putting that out there. But we know that 68% of the universe is made up of dark energy. We know that 27% of the universe is made up of dark matter, which is this weird matter that we can't see. We can't observe it directly, but we can tell that it's there based on the motions or based on the way it gravitationally interacts with visible matter that we can see. And this visible matter only makes up 5% of the universe. I'm sure that you might have heard that before, that things that we see don't actually make up a lot of the universe. All of those galaxy clusters I was showing you earlier, all of these things, all of the light coming from those only came from 5% of the universe. But it turns out it's actually even less than that, because this is a model that is based off of cosmological measurements of various things like the cosmic microwave background, so this is our current working idea of what the cosmology of our universe looks like. However, when we actually try to take observations and try to see, okay, if we look at a galaxy, what fraction of this galaxy is like dark matter versus what fraction is visible matter, what we actually find is that there's a large deficit in the amount of visible matter that we see from galaxies. When we're just like counting up all of the stars that we see, when we're just measuring all of that light, that actually accounts for much less than 5%. So this means that there's a lot of visible matter in the universe that we're just missing. We're just not seeing it. This is also called the missing baryons problem, because you can also call visible matter baryons. Just fancy science words. But yeah, so where is all of this? Where is all of this visible matter that is apparently not visible to us, or not easily visible, I should say. So that is kind of the second question that my research is really trying to address. So wouldn't it be really cool if we could try to somehow address both of these questions at the same time? Yeah, it would be. So how can we do that? Well, we've been talking a lot about galaxies and what lies within galaxies themselves, but what if we look outside of those galaxies and look at whatever else exists in those dense environments? Because surely there has to be something else, right? And it turns out that when we look at galaxy clusters, we actually do see something else there. So what this image is this is a optical image, so something that you would be able to see with your eyes with X-ray data overlaid on top of it. That's what this basically purple light that you're seeing is. This is all data that is visible in the X-ray regime of the electromagnetic spectrum. So it's really high energy, and the only way that we would see that is if there is some really hot gas that was emitting all of those X-rays. And the fact that we kind of see this very smooth distribution of it tells us that, okay, in these galaxy clusters, outside of the galaxies themselves, there is a huge reservoir of hot gas that is just sitting there. And so what does that tell us? What can we learn from this really hot gas that we see in clusters in the most dense regions of our universe? Well, this can solve our first problem. Remember, our first problem had to do with, okay, why are galaxies in clusters not forming stars? And it turns out that part of that could be due to the fact that because there is so much hot gas in these clusters, galaxies in those clusters, moving through those clusters, are actually going to lose a lot of the fuel that they have for star formation. And stars form in galaxies by having a lot of cool gas that essentially collapses down. But if you have a galaxy without any cool gas, you're not going to get any stars because you don't have any gas to make it with. And so these are a couple of pretty extreme observations of what we call jellyfish galaxies, because here is the galaxy itself, and here is kind of this tail of gas that is being removed from the galaxy itself. And here you can kind of see it's less of a smooth tail and a more of these clumps of cool gas that are being removed from the galaxy itself. And what we're not seeing in these images is the hot gas in these environments that's actually interacting with the galaxy itself and causing all of that hot gas or that cool gas within the galaxy to be removed. And the reason we're not seeing that is because it's really diffuse, and we would have to look at it in X-ray wavelengths like we did here. So see, this is the problem that we run into with a lot of this gas. You can't just look at it with an optical telescope. You have to get a little bit creative. And so we see the effect it has on these kinds of galaxies. The problem is these galaxies are only really observed in galaxy clusters. We haven't really seen a lot of jellyfish galaxies, period, first off. And we haven't seen a lot of jellyfish galaxies in less dense environments, such as galaxy groups. So that's one caveat. But in clusters, we can say, hey, this hot gas probably is playing a huge role in stopping star formations in galaxies in clusters. So this solves problem one. What about problem two? Well, the reason why this solves problem two is because now that we're able to actually see more of this hot gas with X-ray wavelengths, we can say, aha, there's our visible matter that we were looking for. And if we count the number of baryons, or if we count the amount of visible light or visible matter that exists in this hot gaseous state, that actually ends up making up for that weird deficit that we had in the missing baryons case. Now that's all great and dandy. We've solved it. We did it. Great. Excellent work, everyone, except for the fact that this is only talking about galaxy clusters. We don't really see a lot of this hot gas whenever we move to other environments, such as galaxy groups. We don't see that. And that could be for a lot of different reasons. Galaxy groups could just have gas that's not hot enough for us to easily be able to detect with our current X-ray telescopes. Maybe we could see it if we built a really sensitive space telescope that we could point at these galaxy groups and say, hey, there's that really not cool gas, but cooler gas that we were looking for that's affecting these galaxies. But the problem is right now we just can't see it. And that's a bummer. And so, yeah, kind of like what I was saying, gas in groups is likely not hot enough to be easily observable and thus very difficult to measure. So what we're showing here in this plot, what we have here on the x-axis is just the mass of these environments. So here we have these really massive galaxy clusters, and this dashed line, well, what we have on the y-axis is essentially the fraction of visible matter that we're observing. And we have this expected fraction, this universal baryon fraction, if you will. What this really is the expected fraction of visible matter that we would expect to see in these environments. And we see that at these really high mass environments, we see all of the visible matter because we can see this really hot gas. But when you go to things like galaxy groups, which is what is down here, it gets a lot more difficult to account for all of these missing baryons. Where is all this missing mass essentially? Because we're not seeing this gas. So what's going on? Well, we have to be able to measure the amount of gas in galaxy groups in order to determine that. But like I just said, we can't really do that right now because we just can't see it. So how are we going to measure that gas? Well, that's a really good question. Now let's talk about active galactic nuclei. So keep that question in mind. We're going to go on a quick tangent, but then we're going to bring it back. So active galactic nuclei. This is just a really long, scary science word for a supermassive black hole at the center of a galaxy that is essentially really hungry. That's just really gobbling up a ton of material really, 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 really quickly. And so all galaxies that are on the more massive end typically have supermassive black holes towards their centers. We see it in this galaxy, we know this in this galaxy as well. They look very different, but they share this one common thing. In fact, even our own Milky Way has a supermassive black hole, as I'm sure many of you know. This is just kind of a cool video that is looking at stars towards the center of our Milky Way. And the reason why we know there's a black hole there is because over years and years and years, we've taken observations of these stars and we see them moving rapidly around some weird thing in the center that we can't quite look at. But if we look at the motions of these stars, we can measure how massive that thing is. And it turns out when we measured how massive it was, the only thing that it possibly could have been was a supermassive black hole. And more recently, I'm sure you all are aware, the Event Horizon Telescope was able to image a supermassive black hole, the one that's in this galaxy, as a matter of fact. So we know they're there. And so they're really cool. And what is particularly cool are when they are in the state known as an active galactic nucleus, or an AGN. Because when you have a supermassive black hole, it's already a huge black hole at the center of a galaxy. But when you have that black hole essentially gobbling up a ton of material from its surroundings, what tends to happen is that as it consumes this large amount of material, it's going to release a large amount of energy into its surroundings. Now, astronomers are super interested in active galactic nuclei for all sorts of reasons. Some of these have to do with maybe the AGN in a galaxy could be what's responsible for shutting off star formation, or maybe the AGN in the galaxy, in one galaxy, is what's responsible for making gas in galaxy clusters so hot to begin with. That's how much power these things have. They're huge. So again, here are a couple of different images of what an AGN might look like. So over here on the right, we have a spiral galaxy. So I think this is kind of a combination of a lot of different wavelengths of data. But yeah, you have this spiral galaxy that we're kind of looking at on an angle, so what we would call edge on. And you can kind of see these large plumes here that are erupting kind of on either side of the galaxy. And those large plumes are likely due to an AGN pushing that gas outside of the galaxy from the center. And so that's what we're seeing there. And before I move on, I will note, whenever I started studying AGN when I first got here to grad school, and I was just fully, I guess overwhelmed is the right way to put it, because AGN come in a huge array of shapes and sizes. If we thought galaxies came in all kinds of shapes and sizes, it turns out AGN are also all over the place, because there are so many different ways you can detect an AGN. For example, you might be able to see it really easily just by looking at this galaxy. You can tell, oh yeah, there are these huge plumes of gas outside of this galaxy. Something's got to be moving them out of there. It's probably because there's an AGN there. Or you can see AGN that look like this. Now this image looks a little bit different from a lot of the other ones that we've looked at, and this is because this is an image taken at radio wavelengths. A lot of AGN are only visible at radio wavelengths, and that's because you see this kind of emission that's happening here. So the galaxy itself would be like kind of around here. This would just be the size of the galaxy. But these AGN jets in radio wavelengths extend far outside of the galaxy itself, which is why people think it can heat clusters. And the kind of emission that you're seeing is this special kind of emission that is emitted when you have high energy electrons that are rapidly going around magnetic fields. It's called synchrotron radiation. And if you're a fan of sci-fi like me, you might hear the word synchrotron radiation being thrown around all the time because it sounds really fun and sciencey. But that's really what it is. And the best way to observe synchrotron radiation is by using a radio telescope. So I am a radio astronomer. I love looking at these kinds of AGN jets because, like I was talking about earlier, it's really interesting to kind of see this interface between the galaxy itself and its surroundings. And what better way to do that than literally looking at jets that extend far outside of a galaxy itself and seeing what happens with between those jets and the environment. So that brings us back to our original question. Hopefully you haven't forgotten it yet. But how can we measure the amount of gas in galaxy groups? Well, it turns out we can observe the effect that that gas has on these radio AGN jets. So the exact image that I was showing you earlier, a typical AGN jet looks something like this. You have your galaxy here in the middle. This is where the AGN itself is. And on either side, you have these huge plumes of jets, these huge things that are basically extending outside of the galaxy itself. And they're really collimated because this is, again, these are really high energy jets that we're seeing being blown out of the galaxy. So they generally look like a straight line. However, a lot of AGN that we find in environments such as groups or clusters don't look like that. What they actually look like is they look fairly curved. So over here we have in black and white, this is just an optical image. And then we have these contours of the radio emission from the jets. And then this is just a circle that somebody drew through the radio emission, just to kind of show how smoothly bent these jets themselves are. And so here we see this bent jet, and then this is actually a simulation of this kind of bending. And so what we see here, it's kind of weird to look at, but this bright emission here, this bright emission, this is the jet itself. And then you have a lot of this other kind of darker red stuff, this is just kind of the cloud that the AGN jet has left behind. But these are the jets themselves. And again, we see this bending of these jets. So what's going on? Why is that happening? Well, it turns out that this could very likely be happening because these AGN jets are moving through some really dense hot gas. So for example, here is another bent AGN laid on top of an optical image that you can't really see that well, but it's fine. So this red circle here is the location of the host galaxy. So this is the galaxy that's hosting the AGN. And then you have these white contours that show the radio emission. So this is the jets that are extending far outside of the galaxy itself. And what's essentially happening is this galaxy is moving in the direction of the arrow through this dense medium, which is very artistically shown with this weird little blue cloud. And as it moves through that dense medium, these jets are actually being pushed back by all of the gas that exists here, all of this gas that we can't really directly see. It's kind of similar to a kid with a little sparkler running around with it. You see like the kind of sparkly bits kind of fall behind the sparkler, and it kind of makes it look bent backwards. This is similar to what we're seeing here. It's literally just an effect of the jet moving through a dense gaseous medium. And it turns out that we can use observations of these bent jets to find out just how dense that gaseous medium is. And if we can find out how dense that gaseous medium is, we can essentially find out how much hot gas there is in the environment of these jets. So this is basically a roundabout way of observing the amount of gas that exists in environments with bent jets, such as galaxy groups. So this is kind of like a nice alternative measurement that we can make without having to upgrade to super duper fancy X-ray telescopes, because those are very expensive and hard to make. And so what does it take for us to actually make this measurement? Well, first ingredient is radio observations. Like I said, these AGN jets are primarily observed in, you can only really see them at radio wavelengths. So we need to point a radio telescope at them. Here is a very pixely image of one of these bent jets. So where the star is where the actual host galaxy is. And then the jets themselves are being bent backwards. And so so again, remember the host galaxy is likely moving in this direction through this dense medium. And the things that we want to measure are the thickness of the jets. It's really hard to see here, but perhaps if I go back here, this would essentially be how thick the jets are about right here. We want to measure that. We also want to measure the radius of curvature of the jets. That's kind of why we want to draw this circle around the jet emission. This will essentially tell us how bent back the jets themselves are. If you have a smaller radius of curvature, you can imagine that they're really bent back. However, if it's big, there's only moderate bending. Excuse me. And we also just want to see how bright these galaxies are in general at radio wavelengths, which is why we would want to measure the total jet luminosity, which is literally just kind of counting up how much light we're seeing at these radio wavelengths. So those are kind of all of our ingredients that we get from our radio observations. However, we also need to know how quickly the jet is moving through the group. And to do this, what we use are optical observations. So specifically, we use spectroscopic observations to determine where all of the neighbors are to our bent double, or to our bent AGN. So we have our bent AGN, beautiful radio data right here. if we zoom in, or zoom out, I should say, a whole lot, in the center is where our radio contours are. They're really hard to see. But we see a lot of these circles here. And so these circles are indicating positions of galaxies that are likely neighbors of our AGN right here. And when I say they're neighbors, what I mean is that they likely exist in the same galaxy group. And so by identifying these neighbors, we can determine what kind of environments they're in. And then what we can do is measure something called their redshift, which is essentially how quickly they're moving in their characteristic environments. So all of this color coding is just kind of color coding whether or not these galaxies are moving towards us or away from us and how quickly they're doing that. And so by measuring the characteristic motion of galaxies in this group, what we can then do is extrapolate that and say that that is likely the velocity that this galaxy here that's hosting this AGN is moving. So a lot of measurements that we have to make, a lot happening here. And so these are all of the ingredients that we need to make this measurement. And now that we have all of these random numbers, which is basically all these are just numbers that we're measuring, what do we do with them? And stay with me. We have one final step, okay? And our final step is to put them all together into physics. You don't have to worry about what this equation means. All this equation is saying is this is a physically derived equation that essentially says, hey, we can get the gas density if we have all of these ingredients that I outlined before. I know I said I wasn't going to put any, equations in here. I'm sorry. All you need to know is that this is how we can measure the gas density. We're done. And then once you have that density for one of these galaxies, you can then carry out this same exact kind of analysis on a much larger sample of galaxies. And so that's essentially what we're planning on doing, is taking this kind of analysis and extrapolating it to a huge set of galaxies that host AGN with these bent jets. So here are some radio observations of a few of the galaxies in our sample. And what we find from some preliminary measurements indicate that there is, in fact, a large amount of gas that resides in galaxy groups. It's almost comparable to the amount of gas that you would expect to see in a cluster. And so because there's so much gas, this could then answer our two questions, which are, what is responsible for making galaxies in these environments not form stars, and why aren't we able to easily see a lot of the visible matter in these environments? And the answer being, because it probably exists in this hot gas. And so currently, the current, I guess, location of where I am in writing my thesis is I have this huge sample, and so I'm just kind of collecting data and I'm reducing data to kind of carry out this sample on, say, over 100 other galaxy groups. So we can kind of widen our sample for which we know how dense this gas is, and thus learn a lot more about galaxy groups themselves. So yeah, this is just kind of a summary slide, which main takeaway is we can use AGN to and essentially look at how gas in these environments interacts with these AGN jets to then learn about the gas itself and the environments itself. We don't have to rely on directly observing the gas. So yeah, that's kind of the summary. So I guess if anybody has any questions, I want to thank you all so much first for inviting me. I was really excited to come out here. And yeah, anybody has any questions?
Yes, I have two questions.
Yeah.
First question, I assume that this requires, since it's radio wavelengths, very large scale sort of interferometry measurements to get the resolution you need. So this is
It
probably
definitely does.
a big project in terms of, there's quite a few investigators involved in this. And you might want to say something about that. And the
Yeah,
second
I'd
is
love
I
to.
couldn't help but wonder more about those bullets that you mentioned in the McDonald Observatory.
Oh, yes. Okay. I was like bullets. No, yeah, absolutely. So first off, first question. Yeah, we do rely a lot on interferometry. So a lot of the data that I'm using is from what is called the Giant Meter Wave Radio Telescope, or the GMRT. And this is actually a huge array that exists in India. And so a lot of our initial observations are coming from there. This is actually some, not observations that I took myself, but observations that were kind of some archival observations that I was working with. And sad story time, I got this huge grant to go out and visit the telescope itself and like take these observations myself. I got that grant late 2019. My observations were planned for mid 2020. You can guess what happened. So yeah, unfortunately I wasn't able to go take them, but fortunately we're still able to get the data. So it's there. I just had to stay here. I didn't get to do any fun traveling. But yeah, so that's where most of our data is coming from. We do have some data coming from the very large array in New Mexico as well. So we're kind of pulling data from all over the place. And we have a few different studies that we're doing. So the first study that I'm working on is actually looking at the environments of these AGN, like without even necessarily carrying out this full measurement of how dense the gas is, and just looking at, okay, are these AGN more likely to be in groups, which they are, but also what do these environments look like compared to AGN that look like this? And so that's kind of step one. And a lot of those AGN were actually, or a lot of that data was actually taken from large all sky radio surveys, taken with the VLA. So yeah, thankfully, thanks to those kinds of huge radio surveys, we're actually able to identify a ton of galaxies that have like AGN with bent jets. Sorry. So yeah. So yeah, we're using a lot of interferometric data. And the reason why we want to reach such high resolution too is, as you can see from this image right here, these jets are generally really, really thin. And so one of the measurements that I mentioned was we want to see how like thick those jets are in order to like determine the density of gas. And so in order to do that, we want to be able to actually resolve this density or this thickness. And so what we need to resolve that is basically a really, really, really big array, which is why we use interferometry. So yeah, hope that answers the first question.
Yes, thank you.
Yeah. And then question number two. So the McDonald Observatory has been around since or like early 1900s. And I think sometime in, what was it, in the 1950s or something, there was an astronomer. Okay, well, first off, for more context, the McDonald Observatory is in the middle of nowhere. Like really, there's nowhere. Like I remember my summer there, I was really curious. So I looked up where the nearest Walmart was. It's literally 99.7 miles away from the McDonald Observatory. So there's nothing there. So now imagine the middle of nowhere, Texas in the 1950s. There was even less stuff there. And so the people that work at the observatory, they literally live in like a tiny neighborhood that's at the base of the mountain. And I guess what happened was somebody got hired there who maybe wasn't of the most like, maybe wasn't in the greatest state of mind to be working in the middle of nowhere, and got really mad at the person who was like the observatory director. And he thought, okay, I'm going to show them, I'm going to shoot the biggest telescope we have, and it's going to shatter and it's going to ruin everything. And so what he did was he marched up to the mountain. he demanded that the observer that night basically lower the telescope so that he could aim his gun at it and shoot it and destroy it. But what he didn't take into account was the fact that when you have a really giant mirror, it's not just like a thin piece of glass that can just be shattered. It's like really freaking thick. Okay. So what happened when he shot it like 6 or 7 times was that the bullets just kind of got embedded in the glass, and that was it. And apparently he got really mad and took a hatchet to the telescope once he realized this wasn't doing anything. But I think at that point he didn't get to do too much damage, because I think at that point they just brought it, the police finally got there and were able to take care of it. But yeah, thankfully no one was harmed. And with the telescope, they literally just filled the bullet holes with enamel. And now it's just a fun story that people at the observatory like to tell. So yeah,
Thank
it's
you.
kind of wild. Yeah, you're welcome.
Only in Texas.
I know, only in Texas, right? It's like so typical. It's so typical.
And for those of us who are familiar with the copying machine from the movie Office Space, that was kind of the frame of mind he was in.
I'm thinking more Yosemite Sam myself.
Oh, exactly. Are there any other questions?
Yeah, Melissa, I was curious about I know this wasn't geared toward this, but in the more denser filaments that you were talking about, do those galaxies actually gravitationally affect one another to the point that that could be accounting for some of the extra heat that they're getting?
So they could be. So here, let me really quickly So are you just saying, oh no.
Yeah, when you were saying that there was all the gases are very, very hot there and
oh, right. So that could have something to do with it. I don't think that interactions between galaxies alone would really be able to account for that quite as much. And I also will say that gas that does exist in those filaments isn't nearly as hot. Sorry, I'm like getting over a bit of a cold. It's not nearly as hot as gas that is actually in these galaxy clusters. So it's all hot gas, but in terms of like how hot it is, I would say gas in galaxy clusters, that's like hot gas. But literally what astronomers call this other state that's not as hot, they call it the warm, hot intergalactic medium. So, you know, whatever.
okay,
So,
thanks.
Yeah, a couple of
Yeah.
degrees higher than you would expect of absolute zero or something like that. Hey, that's really warm.
actually, it is pretty hot. It's actually,
is
so
it?
this gas, oh yeah, also true though. But no, this gas is like, it's hot enough that we would be able to detect it with a more sensitive X-ray telescope. And like to be able to emit any kind of X-ray light, you have to be really freaking hot to begin with. So this gas is really, really hot. It's like still like 10 to the 5 to 6 Kelvin.
Okay,
So
good to
it's
know.
really hot. Yeah, but it's just warm hot instead of hot.
Not as hot as the gas inside your fluorescent light bulb or something like that, or how would it
Oh,
compare
well,
to that?
comparatively, that it's a lot hotter than that, because a fluorescent light bulb is, I don't
Fluorescents
know
are
what
cold.
temperatures it reach, but they're
Relatively.
pretty cold comparatively.
Oh,
Yeah, like
there's-
fluorescent light bulbs. Oh yeah.
Well, the actual temperature of the molecules, you've got a gas, keep in mind, you have a gas that's in a vacuum state. So
Mhm.
the gas itself is extremely hot, like hotter than, I remember a chemistry professor explaining it to us once in lab, that gas was actually hotter than the gas that's in the sun. But the problem is it's not at, the whole light bulb itself is not at thermal equilibrium. So you touch it itself and then, you know, and he was showing us like a vacuum tube, you know, with a fluorescent gas in it that was being excited. I can't remember what gas it was, if it was argon
Yeah.
or something else,
So
but it was an interesting
yeah.
concept anyways.
Yeah, so like for comparison, if you're to look at like just the light coming from a fluorescent light bulb, you would expect to see you're actually a lot of the light coming from a fluorescent light bulb is actually mostly in the infrared wavelengths. And so there's that. And then you're comparing that to like this gas that whenever you observe it, you see it at X-ray wavelengths. And so like the hotter the gas gets, the shorter the wavelength that a lot of the
Right.
light it emits is. So
If you're seeing it in X-ray, you know it's hot.
yeah. Oh yeah. Oh yeah. Any other questions?
So you had started out, right? You're working on like, what was that, 1 or 2 questions, right?
Yeah.
So how long do you think before you're done with your research?
Oh, that's a really good question.
Because I can't fathom doing all this that you're doing, and I'm sure it takes a long time.
Oh yeah, definitely. So like usually PhDs last like 6 years, 5 to 6 years. So I'm like nearing the end of my research, or I guess like my time at UW. I can't say that I'm going to be able to definitively answer any of those questions, but I think I will be able to provide a substantial amount of evidence to kind of point us in a direction that is good, positive.
You're done when your committee
for a lot
says
of
you're
those.
done.
Also that.
And the library
Also
accepts your
that.
thesis.
Yup. You got it. But yeah, so I probably
Asking
have about
someone-
like 1 or 2 more years.
I was going to say, asking someone how their thesis is going is a lot like asking a woman her age.
Yeah, that's why it's always a little fun, especially if you're a grad student that's like me and you're a little bit later on, you're like, So yeah, we're getting there. That's what I'll say.
Yeah, if you're like me, you're just content to develop methods and tools to be able to do, so other people can do further and further research on top of that. And I think a lot of the work is just developing those tools and methods.
Definitely. Yeah, and you know that's something that some people will end up going off to do after their PhDs if they decide like, hey, these are cool questions, but like I'm more interested in like the development side of things. Like people can go off and kind of focus on that instead as well. Or you could even just like, I don't know, I know people sometimes do also just leave the field and like take a lot of because a lot of the tools that you're using here, like I'm dealing with a huge amount of data. And so it's like, you can use a lot of those skills in other fields entirely, like data science and stuff like that. So it's really interesting. Like I have a good friend who's in a computer science grad student, and like we can actually just have conversations because like we understand like where each other is coming from and like the methods that we use. So I mean, obviously he's like on a full other level than I am, right? So it's like I go to him whenever I have questions about things, but it's pretty cool.
Melissa, earlier you mentioned that you were a bit of a science fiction geek too.
Yeah.
I'm wondering, like, who are some of your favorite authors?
Ooh, some of my favorite authors. So, okay, if I'm going to be completely honest, when it comes to reading, I really prefer fantasy. I don't know what it is. Like, I mean, okay, listen, like I do love Douglas Adams, don't get me wrong. But I really am a huge fantasy nerd. When it comes to like sci-fi, I really do just love watching. I like, whenever I was like in high school, I watched like a lot of Star Trek with my family. And even in middle school, we watched a ton of Star Trek, like, like TNG. I love Deep Space Nine, stuff like that. And so I feel like that's kind of played a big role. I would say television and movies influenced my astronomy interest more so than my literary interests.
That's
Like
great.
I said.
The Star Trek reference, I think your credibility in this group just went up a notch.
Yay. I'm glad.
I'm old enough that I watched the original series when it was first broadcast. So
Oh man,
yeah,
that's
I
awesome. That's really
appreciate
cool.
that.
Yeah, that's great.
I remember reading, I forget if it was Time or Newsweek, just before they started showing it. There was a reviewer that was commenting on it, and his he apparently didn't like it because he said it should have been shot on location.
Oh my God. If only, right? Yeah, so easy to do. Hmm. Well, I guess I can go ahead and stop sharing for now. But yeah, no, keep asking questions.
Melissa, great talk. And at the beginning of your
you.
talk, you mentioned having an interest in doing astronomy outreach. And I'm wondering, with what you're doing, with all you're doing, what type of outreach have you been able to do, and what's been the most exciting outreach you've been doing?
That's a really great question. Let's see. I mean, since the pandemic, it's been kind of difficult, which is why I've been relying a lot on this radio astronomy program that I kind of mentioned. That's really easy to do. Like, just write a 5-minute, like, just write a script, record 5 minutes, and send it over to the people at work, and they put it up. So that's been cool, but it is really nice to just like actually be able to talk to people and like show people things. One thing that I've been doing a bit of, that I'm going to start doing again, because Washburn Observatory over at UW campus is going to be opening up again. So I think that's not going to be happening for a few more weeks, but within the next month, it should be open again. So keep an eye out. So I'm excited to get back to being able to do that. One thing that I really loved doing here is Universe in the Parks. Are y'all familiar with that? I see some head nods. I see a lot of like different head nods. So what it basically is where grad students or people at the department, UW Astronomy department, basically go out to state parks in Wisconsin and like all over Wisconsin. And we bring telescopes, we bring a projector, and like one of us gives a talk about whatever we like to give a talk about. And the other one will, after the talk, go on a little star party and just kind of show off cool things. So we do a lot of these at a lot of the state parks that are around Madison, but we also go up to like Door County. I went up to like some of the state parks like way in northern Wisconsin. One of the pictures I actually had was at Willow River State Park, which is really pretty. So we go all over the place, and I really love doing that because like I love the outdoors. And I also just love showing people stuff through telescopes. Honestly, like I'm sure y'all know, like it's like one of the most rewarding things, honestly, like showing somebody like Saturn for the first time and they're like, oh my gosh, are those the rings? I didn't think I'd be able to see them, you know. It's really fun. So that's what I've been doing a lot of. Yeah, I think in undergrad, one thing that we did that I honestly had a really great time with, there were a couple of them. One was we would bring solar telescopes around town, and we would literally just set up in random locations and just like point at the sun. And we'd be like, hey, look at the sun. And we got a lot of people giving us weird looks like, I don't want to look at the sun. I'm not supposed to do that. But yeah, so that was a lot of fun.
The MAS actually used to do that up at the farmers market.
That's so
back in the
fun.
1990s, yeah.
That is so much fun. I've honestly thought a little bit about that. I think that would be so much fun to do at the farmers market here. That would
You
got to
have enough sunspots though to make it look interesting to your telescope.
No, yeah, that's
It's
true.
been a
Otherwise, it's
little
really
sparse
boring.
lately.
Yeah.
Set up right next to the creationist.
Yeah, I was kind of exactly.
Yes.
Yeah, explain to me how that's more than 6,000 light years away. No, one of the things I wanted to mention, Melissa, is that MAS, I'm not sure if you're aware, but we do an awful lot of public outreach too. And so if you're in the area and if you're looking at our Facebook site, we've been kind of putting it on a hold for the last couple of years simply because of everything that's happening. It's kind of hard to have little kids come up and looking through your telescopes, without and worrying about contracting something. But I think we're going to be getting back into that mode pretty soon. But we'll do things out at Donald Park and up at Devil Lake and also the Monona Terrace. Moon over Monona is one of our big events too.
That reminds me, I'll have to try to get a hold of Devil's Lake, because it's been a couple of years since I didn't hear from them at all last year, of course. So we'll have to let them know we're still here.
Yeah,
Yeah.
exactly.
Melissa, come to those if you want to come and do some outreach with us.
Heck
They're
yeah,
always
I'll have to
welcome.
keep updated with everything that y'all are doing. That sounds like so much fun.
It is.
Yeah, typically
awesome.
we'll, for Donald Park, we'll aim for the big meteor shower, the I'm
Perseids.
thinking
Oh, the
wrong,
Perseids?
Perseids. Thank you, Perseids, because the word that was popping into my head was Pleiades over and over again, and I couldn't get out of it. But yeah, so yeah, the Perseids in August, and then we'll usually, in the past, we've aimed for a star party at Devil's Lake around one in May and one around August.
That's really cool.
And then, yeah, then we have usually have moon over Monona Terrace around October. Hopefully,
That sounds like so
hopefully
much
as
fun.
early as possible. But yeah, we search. Usually, typically, we'll aim for a weekend that has a quarter moon, first quarter moon, because people really like looking at the moon and aren't so enthralled by looking at the faint fuzzies that get me thrilled, frankly. But
I understand.
well,
That's really cool though. No, yeah, I'll definitely have to check that out.
well, thank you so much, Melissa. It's really, in addition to telling us all about the really neat research, and frankly, we get a lot of presentations, and it's really neat to hear, a new angle about studying galaxies. I can't remember anything remotely like this since I've been a member. So thank you not only for sharing that research, but also sharing about yourself and your background and telling us a little bit about your story. I think it's really, really fun and inspiring for all of us to get to know you. So on
Great
behalf of
talk.
Madison Astronomical
Very good
Society,
talk.
thank you so much.
Oh, thanks, y'all.